Okay, so welcome back to the GGI lectures by young researchers. Today we will continue with Luigi Tizzano discussing generalized global symmetries and anomalies. Again, feel free to unmute yourself and ask every question you want. So, Thank you, Luigi. Please go on.
Okay, so yes, thank you very much, and thanks for being back and for resisting my lectures. So let's just make a little recap of what we said last time, just very briefly. Last time we discussed that the notion of GP symmetries, so this thing we call generalized global symmetries, and we associate them to some codimension P+1 topological surface operator. Okay, and in addition, we discussed the concept of symmetry breaking very briefly. Which applies also to all these higher form symmetries, which so applies to. And we saw some consequences of this for the various phases that theories can show. So this is related to phases of QFT. And we discussed how important is to couple these GP symmetries to background gauge field. And using this, we were able to say various things about toothed anomalies. And finally, we discuss how toothed anomalies puts constraints on the infrared dynamics. Okay, so this is what we did last time. And today we are gonna use all of these things and combine them to prove some interesting results about Yang-Mills theory. So let's get started. So the main player today is pure SUN Yang-Mills theory. Let's write the Lagrangian so that we are all on the same footing. So there is the standard kinetic term. Sorry, let me. And there is a theta term, which is F wedge F. Now, very importantly, this theory has this parameter theta, which is periodically identified. And right now, let's take this as a fact, but we'll be back and talk much more about this fact, but right now this is a fact. And so once we have this theory, we want to discuss what symmetries does this theory have. So what are the symmetries? Again, I only want to talk mostly about global symmetries. So, okay, what are the main degrees of freedom in this theory? We know that the main degrees of freedom are gluons, which transform in the adjoint representation of SUN. Okay, and so this fact alone will be enough to already understand the first statement for today, which is that SUN Yang-Mills theory has a one form, sometimes called electric symmetry, which in my notation I will denote by Zn with superscript 1. Okay, so let me try to motivate why this is true and why this is related to gluons, okay? Okay, so what's the idea? The idea is the following. Imagine that we put a very long Wilson line. So this extends, say, this extend from -infinity to +infinity. And we surround this Wilson line with some huge surface sigma, okay? So we will be able to measure the charge at either or at plus and minus infinity. So we want to measure the charge here. Okay, so first of all, what is a Wilson line? Let me just remind you that. So a Wilson line is I'm gonna place this in the fundamental representation. Is the following object. So F denotes the fundamental, is the trace over the fundamental of the exponentially path-ordered exponential integral of I integral of A. So A is the gauge connection. Okay, so in general, if you insert this thing and in your theory, this will produce some back reaction, which is very complicated. And so this will affect the gauge field. But again, as I said, we can try to measure the charge at infinity. And the basic fact is that the charge that we are going to measure at infinity is measured modulo n. This is a very important fact. And this is because, okay, when you insert this Wilson line in the fundamental representation, there will be gluons which could screen this line. But in the end, they will not be able to do that because gluons transform in the adjoint representation, while this Wilson line is in the fundamental. So the two things cannot go together. And so it's impossible for us to screen the fundamental Wilson line with gluons. And so that's why we can only measure the charge at infinity only modulo n. So this modulo n is a very important fact. So let me just say more things about it. There's actually a simple, there are some simple mathematical facts that we have to remember. So any Wilson line is, in this SUN theory, is associated to various representations of SUN, okay? And these are all constructed from, boxes, if we think about, Young tableau representation. So the fundamental of SUN will be one box, and then we can construct things like the symmetric with two indices of n, which will be something like this. And then we can write the antisymmetric, which would be something like this. And then, of course, for example, our favorite, the adjoint, which something like this. Okay, so it's a fact of SUN that in SUN there is something that is the center of the group, which we parameterize as some parameter lambda times a n by n matrix, where so an element of the center is parameterized by this parameter lambda, where lambda is equal to an exponential of 2 pi I k over n, where k is an integer. And there is a very important concept in, this is just a concept in group theory of n-nality. Okay, so what is the n-nality? Is the charge under the center of SUN. which is nothing but the number of boxes, modulo n. Okay, so the anality takes value in Zn, of course, and so let me just, for example, the fundamental as anality. Sorry, let's do it like this. Anality, the fundamental. I should do this. Sorry, I'm a bit sloppy. Anality, prep. The fundamental as anality 1, this symmetry with a anality 2, and so we can go on. And in particular, the adjoint as anality 0 mod n. And so this is very important because all the fields that we have in SUNY Mills transform in the adjoint. And so the only way that they can act on anything and screen anything is to add modulo n boxes to the representation that we are studying. And so in this context, anality is a good quantum number. And that means that because we have this quantum number is associated to a global symmetry that acts on the theory, and the global symmetry is precisely this higher form global symmetry. Which is associated, you see, with this parameterization that we made of the center of SUN. So in fact, in the old days, this was called the center symmetry of Yang-Mills theory. So the study of these things is actually very old, and many things were already known since the 80s. And so oftentimes when you hear that SUN Yang-Mills has a one-form symmetry, you could just translate this new statement into saying that this is just the center symmetry of Yang-Mills that was discussed in the 80s. Okay, so these are just some group theory facts. But since now we have a global symmetry, again, as we did last time, we have to ask how it acts and how it acts and what are the charged operator under this symmetry. But we already know that the charged operator will be Wilson line in some representation R. And then what we can do is to surround this line. We will surround this line with some codimension 2 operator. And this operator, you remember, this is the topological surface operator that implements the higher form symmetry. This exists even though the symmetry is discrete, so there is no current conservation needed to do any of this. And the action of this operator on the line, on the Wilson line in the representation R, will spits out a phase, which is I times alpha times the n-nullity of the representation R. So you could imagine, so if you act with this topological surface operator, again, you could shrink it and you will have a new line L up to this phase here, where alpha is 2 pi k over n. So in fact, for the fundamental representation, so for a Wilson line in the fundamental representation, you see that the n-nullity is 1, and we have an action that is precisely correlated with the center of SUN. Okay, so this is basically the basic idea. And so you might ask, so as we said in the Lorentzian interpretation of this story, we said that a one-form symmetry acts on strings. And so you might be asking, what does it mean? Like, where are strings in SUN Yang-Mills? But this is actually very known physically, that so more physically, we should think that this higher form symmetry Zn1 acts on so-called flux tubes. And so these in fact are observed on the lattice. And I think there will be some lectures about lattice quantum field theory in the future in this series. And so stay tuned for that. And okay, so what does that mean? That, you know, we have some Wilson line at some fixed time and we can act with it. And we can construct these tubes. And these tubes are they are protected under this symmetry. So this is the really cool thing. So this is somehow a modern way to think about why these objects are important, because whenever you create one such object in Yang-Mills theory, in pure Yang-Mills theory, this object will be protected under this symmetry. And so it will cost infinite energy for you to have it decay. And so it's not going to decay. It's completely stable. So you could motivate that these objects are stable in pure Yang-Mills because they are protected by the Zn1 symmetry. And so later, in fact, I'm going to tell you what changes when we upgrade to QCD. In QCD, the story is different. And it will be very important. Okay. So first of all, we now know that even though pure Yang-Mills theory is some theory that we know and love, well, we don't know so much about its infrared dynamics, but we know it's Lagrangian. We can write down everything. And now we know that there is this interesting global symmetry. And so we want to exploit as much as possible its consequences. And of course, there's also another important symmetry, which is a discrete space-time symmetry, which is time reversal. And the important point for us today is that time reversal acts on the theta parameter by sending it to minus itself. And this is due to the fact that if we write f wedge f in this way, acting with time reversal on the individual fields will produce basically shifting the Levi-Civita tensor by a minus sign. And so we interpret that as saying that theta goes to minus theta under time reversal. And so we can ask, when is time reversal a symmetry in pure SUN Yang-Mills theory? And the answer is very simple to work out. It's clearly a symmetry at theta equals 0. So of course, at theta equals 0, we act with t, and the action of Yang-Mills theory is time reversal invariant. So this is obvious. And the slightly less obvious point where this theory is time reversal invariant is at theta equal pi. And this is due to the fact that you remember that theta is identified with itself modulo 2 pi. And so this implies that theta equal pi and theta equal minus pi are the same. So we know that there are now two symmetries that we have to think about. One is this higher form symmetry, which is discrete and it's connected to the center of SUN. And then there is time reversal, which is only a symmetry of pure SUN Yang-Mills at theta equals 0 and at theta equal pi. And we'll see many interesting aspects connected to this. Is there any question on what I said so far?
Sorry, I have a very stupid question.
Yes.
So I'm confused about why Zn is a global symmetry when it was part of SUN, as in it's the central subgroup of SUN, right?
Yes.
So why are we not gauging it in some way?
Yeah, that's a very good question. And I'm going to explain what it means to gauge a one-form symmetry very soon. And you'll see it's, so the basic thing is that even though Zn is the center of SUN, it is not actually gauged. And I'm going to discuss what it means to gauge this Zn symmetry. It has a precise meaning, which I'm about to explain.
Okay, thanks.
Is there any other question? Okay. So let's go down this path, okay? With the natural question. The natural question, which is, and this is a natural question in basically any problem that you have in physics. When there is a symmetry, you should always ask this question: how do we couple the one-form symmetry to a background field? Okay, because we know that once we are able to do that, there are many other things that we can say. But in order to understand this question, we need again to dive a little bit into mathematics and discuss the following thing, which is the properties of bundle topology, which in a sense, it's the difference between SU2 versus SO3. And then we will upgrade this discussion to SUN, okay? So I want to discuss what is really the difference between bundles of SU2 versus bundles of SO3. So let me remind you that SU2 bundles are labeled by the instanton number, which is I, which is 1/8 pi squared, integral of m, trace of f with f. Okay, and so this is an integer. And this is precisely the factor that multiplies theta in the Yang-Mills Lagrangian. And when we say that we are performing, when we are basically studying SUN Yang-Mills theory, which means we would try to compute the path integral of SU2 theory, what would that mean? It would mean that there are configurations which are labeled by this integer I, by this integer element I, which are instanton sectors, and we would have to path integrate over all the gauge field on and take the exponential of the Yang-Mills action, and this sum labels the sum over instanton sectors, and we know that the instanton sectors appears in the Lagrangian through their coupling with the theta angle. So this is what it means to study SU2 theory. So in an SU2 theory, we sum over SU2 bundles, which are labeled by this integer I. So when I is equal to 0, it's just a perturbative connect. Somehow it's just a 0 instanton sector. And then when I is greater than 0, so 1, 2, 3, you would have to sum over all these instanton sectors. Okay, but now we need to understand what it means to do the same computation on SO3. So remember that SO3, which is SU2 mod C2. So this SO3 is actually a smaller group than SU2 as a Lie group. But the very, very crucial element is that this group has more bundles than SU2. And in fact, so we still have the instanton number, but we now have another topological characteristic class, another class, which is called the second Stiefel Whitney class. So it's some characteristic class associated to SO3, which take value in H2 of the manifold with coefficients in Z2. So this is a Z2 valued. So this omega 2, one more physical way to think about omega 2 is that it is a Z2 valued magnetic flux. So what I mean by Z2 valued is that if I take some surface sigma, the integral of omega 2 will be either 0 or 1. Okay? And so one very formal way to distinguish between an SU2 theory and an SO3 theory is the following idea. So this is a general fact that an SU2 theory, or more precisely SU2 bundles, which are the one that we sum over in an SU2 theory, are special SO3 bundles with trivial omega 2. So omega 2 is 0. Okay, so one way to see an SU2 theory is to think that you are considering SO3 bundle which have trivial Stiefel-Whitney class. Okay, but now we could just say, now we are ready to say what is the path integral of SO3, because now we know how we should sum in SO3. And so in SO3, there are two different sum. There's a sum over this omega 2, which is in H2 of MZ2, and then there is a sum over K. Sorry, not K, sum over the instanton number. And again, so of course, at the level of the action of Yang-Mills theory, we see no difference between SU2 and SO3 because all the degrees of freedom, the way we write the Lagrangian and all these kind of things only depends on writing things in the adjoint representation. So we're never gonna detect any difference. But there are very subtle differences at the level of non-perturbative contribution, because now we see that in the SO3 theory, bundles are labeled by more parameters. And so the path integral is different. There is no, so this really distinguishes an SU2 from an SO3 theory very generally. That in SU2 theory, this omega 2 is a trivial thing, but in SO3 it's turned on and that modifies the sum over bundles. And of course, this is generalized to SUN. So again, you still have, now in SUN, we will have SUN bundles, which are labeled by an integer I in Z. And of course, there will be another group, which is PSUN, which is the just SUN mod Zn. And so in addition, so here bundles will be labeled by the instanton number and this omega 2. Okay. So this is just very general. So the difference of bundle topology will tell us what is the difference between a theory with SU2 or SO3 gauge group. Okay. But now we are ready to understand what it means to to turn on a background field for this one-form symmetry, okay? So the thing, so what does it mean? Okay, let me try to explain this. Okay, so we want to a background for Zn1. And first of all, this is a discrete group, so we will have to turn on a slightly special type of background field because it will be somehow a discrete gauge field. And in particular, this object, which I will denote by curly b, it's an element again of H2 of the manifold that takes value in Zn. Okay, of course, because it has to implement these discrete symmetries, so it has to be discrete value. And so to study a theory, so now what do we have to do? We have to do exactly the same things that we did when we were discussing the dependence of the partition function of background fields. We have to study the SUN theory as a function of this background field B. But what does that mean? It means that we have to sum. So the path integral will be a sum over the instanton sector, where again there will be this integral over the space of field. But now the crucial difference is that the omega-2 of this of PSU2 will be correlated with this background field. So now this B is fixed. So this B is a background field, is not summed over. So this means that when we study a background field for a one-form symmetry, we are secretly, so this equation means that secretly we are looking at SUN mod Zn bundles with, with B equal to omega-2. So we are fixing this characteristic class and looking at a subsector of this larger group of bundles. But now, of course, now comes the question, then how do I gauge this one-form symmetry, right? Because we said, what does it mean to gauge this one-form symmetry? Now it's connected to a background field. And so we know now what it means to gauge this symmetry. Gauging this symmetry would mean summing over B. So now B will not be fixed, but we have to sum over all the values of B. But if we sum over all the values of B, what do we have? We have a theory which is, again, SUN Yang-Mills plus this gauged Zn1. But this is nothing but the SUN mod Zn theory. Okay? Because now, once we render B dynamical, we have to classify all the bundles, not just by their instanton number, but now we have to take into account all these omega-2, this sum over omega-2. We are summing over it, but that modifies the theory. That is not the original SUN theory, but it's a theory with a different gauge group. And so this is very important. So there is a way to study an SUN theory and how it depends on this one-form symmetry by activating this field B. And once we decide to gauge that symmetry, we cannot anymore talk about an SUN theory, but we have to talk about a PSUN theory. Okay. And there are also other reasons why this is true, but maybe we'll be back. So there are other reasons to detect, and that people already understood on how to distinguish between an SUN and a PSUN theory. Maybe we'll save that for the discussion at the end. But this is really the way to think about this problem, because now studying this partition function as a function of the background will produce very interesting results for us. Okay. So now I want to go back for a moment to these questions about the periodicity of theta, because now we need to make a few statements. So let me remind you that we said that the integral I, so this instanton number is 1/8 pi squared integral of M4 of trace f wedge f. And as I said, this center in the action, we will have something like this exponential of I times theta. And as we said, this is an integer. So this really implies that this is the reason why theta is identified with itself plus 2 pi. Okay, but now there is a natural question that we need to ask again, which will modify this understanding, that what happens if we turn on this background field B. So if we turn on this background field B, that means that we have to look at this SUN mod Zn bundles with fixed omega 2. So what happens to the theta periodicity? Okay, and this is a curious mathematical thing that was discovered a long time ago by mathematicians. So once we turn on this background field, this integral, which is 1/8 pi squared trace of f wedge f, it's actually equal to 1/2n times the integral on the same manifold of omega 2 cup omega 2 plus an integer. So in particular, this thing here, it's always not 0. And so in this case, this is no longer an integer number, but it can be fractional. And in fact, long time ago already, we started calling this object fractional instantons. So, but very, very concretely, the fact that the instanton number is no longer an integer means that theta is not identified with itself plus 2 pi, but it has a larger periodicity. So for this group SUN mod Zn, theta, it's identified to itself plus 2 pi n. So you see that changing bundle topology affects the periodicity of theta. And this will be very important for us. So, okay, so the idea is that in order to understand how to couple a background field for this higher form symmetry, Zn, we really need to understand, we needed to understand the differences between SU2 and SU3 bundles. And since now we understand that, we are ready to take and understand various other things about Yang-Mills, just because we can introduce this background field. And so Okay, so before we move on, are there questions on this?
Well, there was a question on why Zn is a global symmetry. So maybe with the bundle story, it should be possible to answer.
This is the point that, okay, so the logic is the following. If you gauge it, so in a SUN, okay, this is kind of a very subtle story. So it's about what do you mean? What do you mean that a theory has, well, what do you mean when you say that a theory has SUN gauge group? Okay, so when you say that a theory has SUN gauge group, you, well, in the traditional Peskin style of term, you never mention or have, you're not saying anything about the center of the gauge group. So if you really want to promote the SUN gauge group to a global symmetry group, then, sorry, if you really want to say that the Lie algebra SUN is promoted to SUN full group, this means that the center symmetry cannot be gauged, because I just proved it for you. I just proved for you that when you gauge the center symmetry, you don't have an SUN gauge theory, but you have a PSUN gauge theory. So whenever someone say that a theory has a gauge group, that's really not the correct way of saying things. The thing that should come before the notion of gauge group is what are the operators, well, the allowed, we could say, Wilson lines in the theory. And of course, if you say that you allow for Wilson lines of a, so the Wilson lines carry charges under the center symmetry. And so the way you, when you say what kind of Wilson line you are gonna allow in this theory, that will determine uniquely what kind of gauge group you have in the theory. So, but that's very different from the definition that we've been always taught when you say, okay, you have SUN Yang-Mills theory, but you see in SUN Yang-Mills theory, that's really just a Lie algebra statement if you want to talk about a Lagrangian and all these kind of things. But if you really want to talk about the center symmetry, you have to be very careful. And in particular, we know that in SUN, when we talk about SUN as a global gauge group, then that means that the center symmetry cannot be gauged. Otherwise, we would be talking about a PSUN theory. There's nothing wrong with that. It's just these are two different theories, so we need to distinguish between them. And anything I said here is true in any dimension with any amount of symmetry. It's a, so the notion of gauge group is very subtle. It depends on the kind of operator that exists in your theory.
Yes, but clearly you have some bounds on the manifolds you have to take to distinguish between these two.
There are some extra thing that happens when you put a theory on certain manifolds, but at the lab, yeah, there are certain things that happens as well, but these are more like decorating the class of operators that you have. So this is, again, this is even more subtle. So maybe we can move this for later. But in everything I was talking about here, I was just talking about the flat Euclidean spacetime and maybe its compactification, but certainly nothing exotic.
Yeah, just a question. For instance, are you able to see the difference if you take these two theories on S4, on a compact S4?
No, well, on S4, the difference between SUN and PSUN is that, as I just explained, is that PSUN has more bundles than SUN.
Also in S4?
Yes, especially on S4. And if you go away from a spin manifold, there are other, you know, somehow this thing gets slightly more fractional in a way, because the divisibility, these are really technical. We can talk about it later.
Yeah, sure. Yeah, sure. Thank you.
Everything I said here, it's completely true for, you know, flat Euclidean R4. So there is no issue or anything that comes in because of the global structure of the space-time. This is really as physical as it gets. Okay, so now we are ready to state and prove this interesting and very, in my opinion, cool results from 2017. So I'll call it a new anomaly, which is the content of this very interesting paper by Gaiotto, Kapustin, Komargotsky, and Seiberg from 2017. So this paper really ignited a lot of activity in the study of these kind of symmetries. And so one of the goals of my lectures is to just make you aware of these results and maybe make you interested about it. And so give you the opportunity to read more papers on this subject. Okay, so what's the claim? The claim is that pure SUN Yang-Mills theory has a mixed toothed anomaly at theta equal pi between time reversal and the center one-form symmetry. Okay, so now what we're going to do is just to prove this statement, because now we have all the tools to prove it. Okay. So first of all, for this proof, because I don't want to do it really too long, I'm going to assume that n is even, but there's nothing wrong with n odd. You can repeat the same proof with n odd, but we should change some stuff. So the proof goes through for n odd as well. Proof holds for any n. Okay, so recall that the action of t on theta sends it to minus itself. That's what we said before. And so as such, if we look at the action, we have exponential of I theta I. So if we look at the point where theta is equal to pi, this will be equal to exponential of I pi I, where this capital I is the instanton number. And so if we act with time reversal, this will send us to exponential of minus I pi capital I. But exponential of minus I pi capital I is equal to exponential of I pi capital I times exponential of minus 2 I pi capital I. Okay, and so notice that we want to connect these 2 points here. So the only way, in order for the theory to be time reversal invariant, and clearly there is no problem when when the theory is SUN and we do not activate any background field, so this capital B is equal to 0, so there is no background for the one-form symmetry. Clearly, there is no issue with this, time reversal invariance because the exponential of -2i pi capital I is just equal to 1. And that's obvious because we just said that an SUN theory with no background field for the one-form symmetry has integer valued instanton number. And so that phase is just equal to 1. And that means that the theory at theta equal pi is time reversal invariant. Okay? Now, here comes the interesting point. However, we really emphasize how important it is to study a theory as a function of its background field. And so let's activate this non-trivial B, which is equal to ω2. Okay, so now we turn on a background field for this one-form symmetry. But if we do that, the moment we activate this background field, there is this identity that we just found due to the mathematician, which is that this phase exponential of -2 pi I capital I is equal to the exponential of -2i pi times 1/2n times the integral of this ω2 cap ω2. And we know that this thing is equal to the exponential of -2i pi times 1/2n integral of b cap p because of this relation here. And in particular, this phase is not equal to 1. So this is extremely important because so let's go back to the notation that I was using when I discussed Hooft anomalies. If I consider the free energy of the theory, I shift theta by 2 pi and I consider it as a function of the background field. And then I subtract it's the one without a shift. These two objects will not be invariant because of this counter term. So the free energy as a function of the background field, when we shift theta and theta that goes to 2 pi, spits out a counter term. So this is a problem because there is no gauge invariance under this transformation. And so now, okay, but we are seeing an issue, but then what we should really care about is the question that we asked in the last lecture. Can we add something to the free energy so that we remove this counter term? Okay, so let's try to do that. So we can try to add a counter term to f as a function of theta and this background field B. So it's something that we want to add to f, and I'll denote it like this: as Ct is equal to 2i pi times p over 2n times the integral of this b cap p. And for gauge invariance reason, this term is only gauge invariant if p is an integer modulo n. And by the way, whenever you see me write this type of terms which include a cap, this is some notation that we need to use because these background fields are not differential forms. And so you don't formally you cannot take a wedge product of these objects, but in your mind, this thing behaves exactly as a wedge product, even though mathematically it's not correct. Okay, so the idea now is that we would want to have something like f plus this f counter term, and then maybe this object, when we shift theta plus 2 pi minus f plus f counter term will be equal to 0. So this is the thing that we want. Okay. So, but that's, let's see what happens. We know, of course, that without a counter term, we are spitting out this minus sign here. And that tells us that very generally, theta and p, when you shift theta by 2 pi, will shift this operation of shifting theta plus 2 pi will shift p to -1 because we spit out this -1 counter term when we shift theta. So if there was an original coefficient p, it's going to shift to p -1, obviously. Okay. And then another important thing that we have to ask is that how does the counter term SCT behaves under time reversal? Because it has a coefficient p. And so if we act with time reversal, I should know how it transforms under time reversal. And the important thing, again, is that this coefficient p under time reversal shift to -p. And that's for the same reason. This is true for the same reason of of theta f wedge f. It's exactly the same reason. Okay. Okay, now we know everything, and so we can try to see if we can restore time reversal invariance. Okay, so the two special points under time reversal invariance are theta equals 0. But for theta equals 0, there is an obvious choice that it's time reversal invariance. It is just to choose that. So if we choose that p is equal to 0, so we basically don't add any counter term, then at theta equals 0, there is no problem with time reversal invariance. This is a triviality because at theta equals 0, we also kill trace f wedge f. And so even if we activate b, there's not going to be any issue with time reversal invariance. However, at theta equal pi, there will be an effect because, as we saw, theta equal pi spits out that counter term. And so that will be combined with this coefficient p. But p changes under time reversal. So in order to find an invariant point, under t exists only if, and let's write it like this, if 2p minus 1 is equal to 0 mod n. So you see, it's just basically the fact that p goes to p minus 1, but then we have to act with time reversal. So, and so if this has to be invariant, we will have 2p minus 1 equal to 0. But you see, this is impossible to satisfy. Because the only way that the counter term itself is gauge invariant is that p is equal to is an integer mod n. So these two things together can never work. And so this is the catch that, let me recap everything I did for you. So if we turn on a background field B for this higher form symmetry, it is impossible to retain time reversal at theta equal pi. But this is exactly the thing that we discussed in the previous lecture. This means that the center symmetry and time reversal have a mixed tooth anomaly. And of course, you can repeat the same logic for odd values of n. The analysis is slightly different, but the conclusion is exactly the same. And so this is something completely general. And it's a very important and striking result that we can prove just based on the fact that we understand the existence of this global symmetry and we can just couple it to background field. It's extremely powerful. Okay. And there is also a way to think about this result in a much more intuitive picture, which I'm going to give to you, which is based on everything I said before about the difference between SUN and PSUN. So let me just give you the intuitive proof. This is the like one-line proof. It's not the one that appears in the paper, but it might be enough if you don't care too much about the details. Intuitive proof. Okay, so we start with SUN Yang-Mills theory. Okay, and so as we know, the center symmetry alone does not have any anomaly, so there is nothing that stops us to gauge the center symmetry. So we can start with SUN and gauge the one-form symmetry. If you do that, we end up with SUN mod Zn Yang-Mills theory. Okay, but now this has consequences because in SUN mod Zn Yang-Mills theory, the instanton number, as we saw, belongs to, it's fractional. It's like 1 over n times an integer. And in particular, in SUN mod Zn Yang-Mills theory, the periodicity of theta is theta plus 2 pi n. And so now there's nothing to prove because the moment that you change the periodicity of theta, there's really nothing to prove because now theta equal pi is clearly not time reversal, sorry, theta equal pi is clearly not a time reversal symmetric point. In SUN mod Zn. That's obvious because now theta doesn't shift by 2 pi, but it shifts by 2 pi n. So there's no way you can connect the physics of theta equal pi to theta equal minus pi. So really, theta equal pi is really not theta equal minus pi. And so this is really the short intuitive proof. There are two symmetries. I gauge one of them, and the other is spontaneously broken. And that's it, we are done. This is a sign of a tooth anomaly. So there are two independent ways to see that these two symmetries cannot coexist at theta equal pi. And now we'll try to derive more consequences of this fact. Because once we have a tooth anomaly, there are consequences on the infrared dynamics of a theory. Is there any question on this? Okay, maybe later then. Now, let's see what we can do with this anomaly. Okay, so we have an anomaly and we want to understand what are the consequences. So what we need to do is to use anomaly matching, exactly as we discussed last time. What does anomaly matching tells us? So 't Hooft anomaly matching forces us with the following fact, that the infrared of Yang-Mills theory at theta equal pi cannot be trivially gapped. And first of all, this is opposed to theta equals 0. At theta equals 0, we do expect that the infrared dynamics is trivially gapped, although there is no, we don't have a proof for that. But the really cool thing about theta equal pi is that now we have a theorem. This is a mathematical theorem. The infrared at theta equal pi will be certainly not trivially gapped. And this is something striking that we can say right away just by the existence of this anomaly. And so what are the chances? What are the possibilities? So there is one possibility, which is somehow exotic, is that the infrared of Yang-Mills theory at theta equal pi is actually gapless. So for example, it could be something like some deconfined theory, could be free, maybe crazy, could be some conformal field theory, but it would have to be gapless in that case. And so this is one option. You could argue that maybe for just n equal to the smallest values of n that we can, maybe this is not ruled out yet by any other consideration. But certainly if you try to study the theory in the large n limit, so for large n, this is not possible. So large n analysis really, we could almost say that it rules out the possibility that Yang-Mills is gapless at theta equal pi. Although for the strict small n values, there is no mathematical proof of this fact. Then there is another option that descends from the fact that the anomaly is an anomaly of finite order, as I told you. So it involves discrete symmetries. So another possibility is that the infrared dynamics is described by some non-trivial topological quantum field theory. And as of the publication of the paper and a little bit after that, this was a viable possibility. So one could come up with some version. One could think that you could find some kind of topological quantum field theory in the deep infrared, which would describe the dynamics of Yang-Mills theory at theta equal pi. But more recently, I think in 2019, this possibility was ruled out completely. So there is now another theorem that says that this thing cannot happen, and by a nice paper of Cordova and Omori. So this we know already that this is not possible. And then we are left with the most compelling scenario, which is the most compelling scenario both from lattice observation and large n analysis, which is that at theta equal pi, the infrared has the time reversal spontaneously broken. And so that means that there are two degenerate vacua, because we are breaking a Z2, so there will be two vacua in the deep infrared, which are exactly degenerate. And this is really the most likely possibility, although, as I said, there's no, it's not that we have a mathematical proof, but it seemed that most of the things that we observe with various techniques, say Largen or holography or lattice, seem to point to this direction. So this is a very interesting thing, and it's reassuring that it's completely compatible with what we see, with something that we know for sure, that there is an anomaly. Okay.
Sorry, can I ask you,
Yeah.
what kind of argument do the authors use to exclude the second possibility?
We will, maybe we leave this for the discussion session.
Okay.
Okay. So let me make two more comments. So first of all, this is really the most striking thing, that nothing in what I said in deriving this anomaly. So, and this is really the most powerful thing at theta equal pi, is a fact, and it's true non-perturbatively. There is nowhere any sign or anything about perturbation theory here. And these are really the most sought after results in quantum field theory. There's no weakly coupled calculation whatsoever that goes into making this type of symmetry arguments. And so that's why they are so powerful. And a less obvious thing, and which will have consequences now for us, is that when we place, so one thing that was very popular, and it is very popular, is to study Yang-Mills theory at finite temperatures. So to study the theory on a compact circle. So, and if we study finite temperature Yang-Mills theory, and this is very unusual, the anomaly persists. What do I mean by that? I mean that if you put the theory on a circle, you can still, you are not able again to remove this anomaly. And this is a very particular thing that happens because this anomaly involves higher form symmetries. And so the intuitive picture is that higher form symmetry couples to higher number of legs background fields. And so when you put these fields on a circle, they would still survive under dimensional reduction. And so you can't really get rid of these higher form anomalies when you place a theory on a circle. And this gives another striking consequence, that using this anomaly, we can also make prediction for the theory at finite temperature. And so that's what I'm going to do next. And because of that, you can draw something that is studied a lot in this business, which is the so-called theta temperature phase diagram. So what does the theta temperature phase diagram look like? It works like this. So we have two axes. One is the temperature and one is theta. Okay. So then we have to just understand various things. So first of all, let's begin from the theta axis, where we now know that, so at theta equals 0, this is theta equals 0, the most compelling scenario is that we have a unique ground state that is trivially gapped, okay? And then we know that at theta equal pi, let me put it upstairs here. At theta equal pi, we have two exactly degenerate ground state. I'm gonna do it like this. So at theta equal pi, two degenerate vacua. And then, of course, when we go back to 2 pi, we have the same physics as if theta equals 0. And in between, so in between, when we tune theta, there are first order phase transitions. So there are vacua that splits. Then, wait, what's going on? And then once we tune that, it's gonna go down, and it's gonna be like this. So moving down here, it's gonna be first order. So first order means there are 2 vacua coexisting and they kind of switch in dominance across some first order lines. Okay. Now let's talk about the temperature line. The temperature line is the line that is, it's been studied a lot in Yang-Mills theory. It's a line that distinguishes between a confined phase and a deconfined phase. So in pure Yang-Mills, we expect that when the temperature is high enough, the gluons are liberated and the dynamics is completely deconfined. So there is some temperature, some critical temperature, which is the temperature of deconfinement. And so below the deconfinement temperature, the one-form symmetry is preserved, because below this temperature, the theory is confined and gapped. Or if you want to phrase this in terms of flux tubes, you know, are stable. Or if we wanted to insert any probe quark to screen these objects, it would cost us infinite energy. That's what I mean by stable. But when the temperature is very high, so this is called a confined phase. Of course, when the temperature is high, the phase is very different, because all these gluons now are freely liberated. They can move, and we have something that looks more like a perturbative theory. And so this is a phase that we call deconfined, which is above TD. And in the picture of flux tube, you could imagine just heuristically that the flux tube at such high temperature starts melting and produce things like that are more similar to plasmas and things like that. So here, the one-form symmetry is broken. Okay, so when we heat up enough temperature, Yang-Mills becomes deconfined and the one-form symmetry is broken. And so let me put this on the right side. Now, lattice people have tried to calculate how this transition here, which is without theta, is a first order transition. They start to study how you can extend this line in this plane. Okay, so we know by lattice simulations that there is a line that extends in the theta plane. So we can extend this deconfinement transition also as a function of theta. And for SU2, the interesting thing is that for SU2 Yang-Mills, this is closer to a second order line. But for SUN, so let's stick to n greater than 2. This is first order. But anyway, we know that there is a line that extends in theta plane. And now there is a very interesting question, which is the following. If we are at theta equal pi, time reversal is spontaneously broken. But we also know that if we start to heat up the system, which means we put the theory on a circle, the anomaly doesn't go away. So there is some line that starts to come up. And at the end of this line leaves the temperature, which tells us when time reversal will be restored, because it's a standard fact of symmetries that if a symmetry is spontaneously broken at 0 temperature, when you heat up the system, it will be restored. So there is some critical temperature where time reversal will be restored. And so the question, so there is something called TCP. And the question is, there is a blob here. Okay, so this is the unknown. We don't know what happens in the blob. So the natural question that we have to ask is, what happens to the restoration of time reversal or CP invariance? Does this line goes above, so cross the transition line of deconfinement or not? Okay, so this is a natural question for which before this paper, there was no non-perturbative argument for it. And so let's see how we can solve this question. So we just need to use the mixed anomaly. So the question is TCP, well, greater or equal or smaller than TD? Okay, so let's start with the options. So option 1 is that that time reversal is restored before that we reach the deconfinement temperature. Okay, so that means that the line would end up here. But this is impossible. This is impossible because time reversal and the one-form symmetry enjoy a mixed anomaly. And so if time reversal is restored here, it would imply, because of the mixed anomaly, that the one-form symmetry is spontaneously broken. But this is impossible because the one-form symmetry at very low temperature is clearly not spontaneously broken. So these two things cannot coexist. So this is extremely powerful. So this is impossible because it's ruled out by the anomaly. So we are only left with option 2, which is that TCP is greater or equal than TD. So the outcome is that time reversal cannot be restored before reaching the deconfinement transition line. And again, this is completely general, completely non-perturbative, and it's a very, very interesting result that we can just put down thanks to this anomaly matching kind of argument. And so it's very striking that we can prove something like this with so little information, but nevertheless, this is true and it's very nice. And so this kind of results have then stimulated a lot of interest in the study of these symmetries in various dimensions and in various other models, clearly, because then once you have a gauge theory, you will start to ask questions like, what are its global symmetries? Are there higher form symmetries? Do they have toothed anomalies? And so this question is, completely general, and many people have worked on this topic and found a lot of cool results that are in this vein. So, and also another interesting thing is that none of these results really rely on special symmetries like conformal invariance or supersymmetry. And so these are fully general things that can also be used in those cases, but they extend beyond the applicability of supersymmetry, for example. And so they teach us very universal things about quantum field theory. Okay, so there is, I think, there's like a stopping point, which is very natural here. And I could say a few more things about QCD, but maybe we can stop, and maybe, I don't know, if you are interested, I can say a few things about also QCD, but maybe you let me know, or maybe you already have a lot of questions and you want to stop here.
Well, yes, I don't know. I'm interested also in the QCD parts. I don't know whether.
Okay, maybe if there is someone who has pressing questions on YAMLs, he can ask them now, and then I'll just say a few things about QCD. Okay, I'll just say a few things about QCD, but of course in QCD, there's gonna be many more subtleties, and the picture is, well, it still needs to be understood, of course. So, okay, what is QCD? QCD is SUN YAMLs theory plus NF fundamental quarks. That are massless Dirac fermions. I'll denote them with capital Psi I Dirac, which transform in the fundamental of SUNF. Okay, so you can think about this Dirac fermion like this in some two-component fashion. Alpha dot, I tilde, okay? And so, well, the standard picture is that for, well, this is the standard picture, but it's far from being proven, or it's a very interesting problem, that for small enough NF, there is something called color screening. And now we understand what it means that there is color screening. There is color screening because there are fundamental quarks. Fundamental quarks have the same anality that we would have if we try to introduce fundamental Wilson line. So things can get screened. And the problem is much more complicated than in pure YAMLs theory. And on top of that, we expect that there is something called chiral symmetry breaking. So we expect that the global symmetry group, which is SUNF times SUNF tilde, is broken to some diagonal subgroup SUNF. And this channel of breaking is due to a non-zero condensate psi I chi j tilde. Okay, well, you can express this in terms of the QCD scale and delta I j tilde. Okay, so, and this is a very important symmetry that is preserved for any value of the direct mass. And so there is some phase structure that we can try to write down as a function of NF. So there is NF, so NF equals 0, we know what it is, it's just pure YAMLs. And that's what we discussed about today. And then there is NF equal 1, which is a very interesting theory. And we believe that the infrared of this theory is gapped. It's trivially gapped. And then there is the theory from NF equal 2 to some value here, which I have no clue, or, well, there is no really, we don't know what is this value. Let's call it NF star. We don't know what it is, where we expect chiral symmetry breaking. And then above this value, there is another window which ends at 11/2 times NC, where the theory here is said to be in a non-trivial interacting conformal field theory phase. Maybe some of you heard this under the name of Banks-Sachs fixed points. But this type of physics is very clear, very close to this window where we can have we can study the Banks-Sachs fixed point in very good approximation. But of course, as you, once you start moving down this conformal window and you start to reach the bottom of the conformal window, physics, so this analysis a la Banks-Sachs is not very reliable. And in fact, the problem of what happens by the end of the conformal window is a notoriously very difficult problem. And okay, so but for today, for the things I want to say right now, I don't want to talk about this interacting CFT phase. I just want to talk about everything below the window. So the theories that we believe are going to confine in the deep infrared. And as I already told you about, there's a problem that because we have fundamental quarks, this means that the theory has color screening. And in particular, it also means that the flux tubes are no longer stable. So by this, so people say that the color, so there's this terminology that the color tubes can snap. What it means now that if I have some quark anti-quark tube, this can be, now it doesn't cost infinite energy to probe it with some quarks, and this kind of things can snap. So they can separate into two mesons. Okay, so basically this already tells us something about our understanding of the global symmetry, that it's clearly not going to be enough to think about the center symmetry here, because the center symmetry is screened by these fundamental quarks. So that's not going to be a useful criteria to try and define confinement in QCD, because clearly that symmetry is explicitly violated by the presence of fundamental quarks. And so in addition, there's also another symmetry which I don't have time to talk about today, which is the U1 baryonic. So this is a symmetry under which baryons transform non-trivially. Okay, so then what you can do is to study this theory as a function of the mass, which we will take as a complex mass where we take the absolute value of m, and then we study it as a function of theta over nf. So this is something that we do to parameterize the complex mass, because in QCD we can always rotate away any theta angle by redefining the mass in this way. So this is, and then you could sit down and try to study the theory as a function of the mass. Okay. So because of all this problem with color screening, we would imagine that there's nothing else we can say much about this theory. But actually that's not true, because it's slightly too quick. Because we can, again, try to think about what are the symmetries that act on the degrees of freedom in QCD. And we can come up with something that is called the Fateful symmetry group. So remember that quarks transform under the SUN gauge group and under this SUNF, and also under the U1 baryonic. But these groups have different quotients that we can perform, because the one form, sorry, the gauge group has a center symmetry Zn. and also the global symmetry group as a center symmetry, which is ZNF. This is just the structure of these groups in terms of group theory. And so we can try to, what we can do is to package this factor here and say that actually the global symmetry group that acts on quarks is not really SUNF times U1, but it's really UNF. And so more precisely, the Fateful symmetry group should be SUN times UNF modulo ZN. Okay, but now we can do something which is really nice, because you see this group now is quotiented by this ZN center symmetry. This comes from the fact that we can perform gauge transformation in SUN, which are in the center of SUN. But what we can do, exactly as we did in pure Yang-Mills, is to activate some background. We can activate a background gauge field for the symmetry group UNF mod ZN. But at the same time, so I'm gonna call this B again. But if I activate B, it means that this I need to take into account the fact that this quotient is also acting on SUN exactly as before. So this means that we again need to consider SUN mod ZN bundles. Okay, and this, I mean, there is some math that we should do here, but I don't have enough time to derive it for you. But the logic is very different. This is just an ordinary zero form symmetry. If we mod it by Zn, it's going to have some characteristic class. We can connect that to this background field B. So again, B will be some omega 2 of this UNF mod Zn. And the moment that we do that, because these quotients appear both on the gauge group and on UNF, we need to take into account also gauge bundle that transform under SUN mod ZNF, sorry, mod ZN, because these both act on SUN and on UNF. So we cannot disentangle the two things. And now that comes back our understanding of the theta periodicity, because of course, if we turn on SUN mod ZN bundle, theta will no longer be periodic as before. That's clear from what we said before. And so we can prove again a cool mixed anomaly. So QCD, so not pure Yang-Mills, will then have a mixed Tooth anomaly between time reversal and the flavor symmetry group. Now, this is not anymore a one-form symmetry, but it's just an ordinary global symmetry, UNF mod Zn at theta equal pi. So basically, using similar consideration as in pure Yang-Mills, we can now find out that what we thought was the ordinary global symmetry group of QCD is a mixed anomaly with time reversal at theta equal pi. And another way to say that is that we extended the periodicity of theta into theta plus 2 pi L, where L is defined as the greatest common divisor of N and NF. And so the anomaly is there unless, so there is not going to be any anomaly if well, if L is equal to 1, if N and NF are coprime. this GCD comes from the fact that when we study the bundles for both groups, there's going to be, we can, you know, turn on some counter term and then try to make the analysis of how we can cancel such an anomaly. And that will require solving certain equation for the coefficients of the counter term. And this equation will have non-trivial solution if and only if this parameter L will be equal to 1. And this was beautifully explained in a paper from 2019 of Cordova, Hotatlan, and Seiberg, but also other papers before. And again, now you can do certain similar consideration. For example, you can study the phase diagram. So these are a few things you can do. You can study the phase diagram of QCD as a function of this M, of the mass M. So remember, M is equal to absolute value of M e to the I theta over NF. And so you can ask yourself about the difference between theta equals 0 and theta equal pi. And yeah, there are interesting conjectures for domain walls in this theory. And you can read more of these conjectures in the literature, but they are based on the fact that because there are two vacua, when theta is equal to pi, there are two vacua which are degenerate. And so you can start asking questions about what are the domain walls that interpolates between these two vacua. And there are interesting constraints that you can put based on the existence of this anomaly. And so there's many more also exciting results also outside QCD, for example, theories with agile matter, chiral theories, which are very interesting. You could study them again in this fashion. And so it's a very active topic. And so I feel that now you have at least a bunch of tools for understanding many of these claims in the literature, and go ahead and try to understand everything better. Okay, so thanks a lot for tuning in, and it was a pleasure. And please feel free to ask any question now.
Thank you very much, Luigi. Are there any questions?
Yeah, I'm just curious about the, like when you showed the fact that theta is not 2 pi periodic when you turn on the background gauge field for
Yes.
Zn.
Yes.
You used a kind of identity which said that f wedge f is an integer, maybe plus the integral of b wedge b.
Yes.
Yeah, this seems a bit mysterious to me. I'm just not familiar with the mathematics, but how would you show just such a thing? Because f is a differential form, but then b is not. I don't know.
No, it's an interesting question. It has to do with the fact that okay, let's go back. Well, okay, if you really want the math proof of these facts, I can try to tell you the intuition, but so remember that so a formal way to talk about this object is to say that there is a C2 of this is like a C2 of an SU2 or SUN bundle.
Yes.
So it's a characteristic class. Okay, now this is a bit abstract, but basically when you turn on this background field, well, when you consider now SON bundle, there is no, basically mathematically, there is no quantization condition for the C2 of SON. It's so you know, SON will have this some other non-trivial. So apart for C2, there will be some non-trivial characteristic class that is omega 2. And so then there is a theory of characteristic classes that connects these objects. And so it's not really, you know, yeah, I don't have like a very intuitive picture. But one place, if you like this kind of details, one place where you can read about it, if you like also a bit of mathematics, it's a book by Donaldson and Cronheimer. It's called like 4 manifolds. And they explain this much better than I can in SU2 versus SO3.
Okay, thanks.
I'm sorry, I don't think I have like, you know, a very clear, intuitive, physical picture at the moment of how to prove this result.
Okay.
But it's very important mathematically though, so that we know of this.
I see.
Other questions? If not, I think we can stop the recorded part. So thank you, Luigi, for the truly interesting lectures. We can